Welcome to the Deep Dive, your shortcut to being well informed. Today, we're diving into the surprising world of chemical bonds, but maybe not in the way you typically think about them.
Right.
What if a bond, something we usually picture as strong, stable, what if it breaks in a totally unexpected way? Not forming ions, but something, well, much more fleeting.
Exactly. We're stepping into the world of radicals. These are species with unpaired electrons. Forget the rules you learned about plus and minus charges, because radicals, they play by a completely different set of rules.
And that's our mission for this deep dive. We're pulling insights from Chapter 37 of Clayden, Greeves, and Warren's Organic Chemistry, 2nd edition. Our goal, to really unpack these fascinating, sometimes elusive species, how they form, why they behave so differently, and maybe most importantly, how chemists can actually harness their unique reactivity for powerful transformations. We're talking building complex carbon frameworks here.
Yeah, and we'll dig into the mechanisms, the pathways, how functional groups change, even a bit of stereochemistry and retrosynthesis along the way.
It sounds like it really flips your usual understanding of reactions on its head sometimes.
It definitely can. I mean, take hydrogen chloride, HCl. In solution, we know it undergoes, well, heterolysis.
Right, heterolysis meaning uneven splitting.
Exactly. One atom, chlorine in this case, grabs both bonding electrons. You get distinct H+ and Cl ions. That's standard ionic chemistry.
But the source mentioned something pretty wild. Imagine HCl gas, heated up, way up, like over 200 degrees Celsius. It doesn't break into ions then.
No, it does something called homolysis.
Yeah.
Homolysis, even splitting. The electron pair in that HCl bond just splits. Each atom gets one electron back.
Ah, okay, so one electron goes to H, one goes to Cl.
Precisely, and the products you get from that homolysis are radicals. Each one now has a single unpaired electron. We show it with a little dot.
H dot and Cl dot.
Yep. And that fundamental difference, heterolysis versus homolysis, that's the starting point for this whole different world of radical chemistry.
Okay, so homolysis is how radicals are born, fundamentally.
Yeah.
What are the main ways chemists actually make them in a controlled setting?
Well, the most important way, the primary route, is the homolysis of weak bonds. The book really emphasizes this.
Weak bonds? Like what?
Think OO bonds, like in peroxides. Dibenzoyl peroxide is a classic example. Or halogen bonds, like BRB. These bonds are just inherently weaker, easier to snap.
And you just need to give them a little push.
Energy-wise.
Exactly. Usually heat or light. Some bonds need serious heat, over 200 C, but others break apart just above room temperature. Light, especially UV light, packs a punch too. That's why some compounds degrade in sunlight.
Makes sense.
And a really common initiator you'll see in the lab is AIBN, isobutyronotriol.
AIBN. Yeah.
Heat it up and it cleanly breaks down. You get stable, nitrile stabilized radicals and nitrogen gas, which just bubbles away, nice and clean.
And the mechanism errors are different too, right? Not the usual double-headed ones.
Good point. Yeah, we use these single-barbed arrows, often called fishhook arrows. They show the movement of just one electron, not the pair.
Okay, so homolysis of weak bonds is number one. What else? Another key way is abstraction. This is where an existing radical bumps into a stable molecule and basically snatches an atom with its electron.
Pulls off an atom, electron, and all.
Yep, so you start with one radical and with a different radical and a new stable molecule. A classic example is an alkoxy radical, RO, abstracting a hydrogen atom from HBr.
So the RO becomes ROH.
Right, stable alcohol. And you're left with a bromine radical, ProO.
And crucially, it's grabbing a hydrogen atom, not a proton.
Exactly. H dot, not H plus or O. And another key difference from ionic stuff like SN1 or SN2, radical substitutions rarely happen directly at a carbon atom this way.
Interesting. Okay, what's method 3?
Addition. Pretty straightforward.
Oh.
A radical adds itself to a stable molecule, usually across a double or triple bond, and you generate a new radical.
Like adding bro to an alkene. We saw that back in chapter 24, didn't we?
That's a perfect example. The bro adds, and you end up with a new carbon-centered radical.
Okay, and there's a variation on that.
Yeah, sort of related is single electron transfer, or SET. Think of it as a reduction. You take a really reactive metal, like sodium, which loves to give away an electron. It can donate just one electron to a molecule with a suitable low-energy empty orbital, like the orbital of a ketone.
And what does that make?
You get something called a kettle radical. It's actually a radical anion. That's a negative charge. And that unpaired electron sitting in the orbital. Really interesting species.
Wow, okay. Homolysis, abstraction, addition, SET. Is that it?
One more main one. Elimination. This is kind of the reverse of addition. A radical just breaks down on its own, unimolecularly.
It falls apart.
Yeah, to form a new, often more stable radical and a stable spin-paired molecule, like the radical you get from dibenzoyl peroxide in Italy. It can kick out CO2 to form a phenyl radical. It sheds a stable molecule.
Okay, got it. Homolysis, abstraction, addition, elimination, the four main ways to make that single unpaired electron appear.
That's the core toolkit for generating radicals.
So now we know how they're born.
Yeah.
What makes them tick? You said they're reactive.
Oh, incredibly reactive, most of them. That single electron is desperate to find a partner, so they usually have very short lifetimes, reacting with almost anything nearby.
But there are exceptions.
Big time. This is where it gets really cool. There are things called persistent radicals. Radicals that can actually hang around for a long time, sometimes indefinitely.
Like stable enough to put in a bottle?
Some are, yeah. The classic example is the triphenyl methyl radical, discovered way back in 1900. It exists in equilibrium with its dimer, but it's stable enough you can readily detect it, work with solutions of it.
What's its secret? How does it survive?
For triphenyl methyl, it's mostly steric hindrance. Imagine those three bulky phenyl rings arranged around the central carbon. They twist up like a propeller, and that physically blocks other molecules from getting close enough to the radical center to react easily. It's like shielding.
Bodyguards for the radical center.
Pretty much. Now, ideal electron delocalization isn't perfect there, but the crowding is key. Other radicals, like tempo or galvanoxyl, are even more stable solids you can buy.
And they use the same trick. Sterics.
They use a combination of steric bulk and electronic stabilization. That unpaired electron is often delocalized over oxygen or nitrogen atoms too, which helps spread it out and stabilize it.
Is there a biological example?
Absolutely. Think vitamin E. It's an antioxidant. What it does is intersect dangerous, highly reactive radicals in your body. It quenches them by donating a hydrogen atom.
An abstraction reaction.
Exactly. And vitamin E itself becomes a radical, but it's a much more stable, delocalized one. It effectively tames the dangerous radical.
Neat. But how do we actually see these things, especially the short-lived ones, and figure out their structure?
That's where a technique called electron spin resonance comes in, ESR, sometimes called EPR.
ESR. Sounds a bit like NMR.
It's analogous, yeah. NMR looks at the magnetic moments of nuclei, like protons. ESR looks specifically at the magnetic moment of that unpaired electron. It's unique to radicals.
So what can it tell us?
A lot. It confirms a radical exists, for starters, but it also gives structural details. Take the methyl radical, CH3. Its ESR spectrum has a specific pattern, a 1.3.3.1 quartet.
Okay, what does that mean?
It tells us that the unpaired electron is interacting equally with 3 equivalent protons. That points directly to a planar structure, Sp2 hybridized, with the unpaired electron sitting in a p orbital.
And that orbital with a single electron has a name.
We call it the SOMO, the singly occupied molecular orbital. It's the radical's frontier orbital, basically.
SOMO. Got it.
And ESR can even show if that electron is spread out, delocalized. Like in the cycloheptate trienol radical, the spectrum shows it's shared over the whole ring system.
So structure is key to stability and reactivity. How do we quantify stability?
Bond dissociation energies, BDEs, are a great guide. The energy needed to break a bond homolytically, XY goes to X plus Y, tells you directly about the stability of the radicals formed.
So weaker bond means more stable radicals.
Exactly. If it doesn't cost much energy to form the radicals, they must be relatively stable.
Is there a trend, like with carbocations?
Yep, a very clear one for alkyl radicals. Tertiary radicals are the most stable, then secondary, then primary, and methyl radicals are the least stable. The energy needed to break a CH bond reflects this perfectly. Tertiary CH bonds are the weakest.
So forming a tertiary radical is easier.
Much easier, and this directly impacts reactions, like which hydrogen gets abstracted.
What about things like resonance?
Huge factor. Conjugation is really important. Allyl and benzyl radicals are way more stable than simple alkyl radicals because that unpaired electron can delocalize into the pi system.
Spreading the load, basically.
Exactly. ESR confirms this beautifully. Contrast that with, say, alkynyl or aryl radicals, where the electron is stuck in an S or sp2 orbital. Those CH bonds are much stronger. The radical's less stable.
Okay, now here's something that sounds weird from the outline.
Yeah.
Adjacent functional groups, like carbonyls or ethers, all stabilize radicals, even if one is electron withdrawing and the other is donating. That seems counterintuitive compared to ions.
It does, right.
Yeah.
But it's true. And we can understand it using frontier orbital interactions, thinking about that SOMO again.
Okay. How does that work?
For an electron withdrawing group, like a carbonyl or a nitrile, it has a low-lying empty orbital. That empty paw can overlap with the radical SOMO. This mixing creates a new, lower energy SOMO. So the unpaired electron drops in energy, stabilizing the whole radical.
Okay, that makes sense for electron withdrawing groups.
Oh.
But donating groups,
Right.
like an ether oxygen.
Right. So an ether oxygen has high-energy lone pairs and orbitals. These can interact with the SOMO too. Now, the SOMO energy itself might actually go up a bit.
Wait, that sounds destabilizing.
But the lone pair electrons in the oxygen orbital drop significantly in energy due to the interaction. The overall energy of the system goes down, so it's still stabilizing.
Wow. So both withdrawing and donating groups help, just through different orbital interactions.
Precisely. And if you have both an electron withdrawing group and an electron donating group attached to the radical center, that's especially stable. We call those captative radicals.
Captative.
Okay. The big takeaway is pretty much anything that stabilizes a carbocation or a carbanion withdrawing groups, donating groups, conjugation will also stabilize a radical, just via these SOMO interactions.
That's a really useful rule of thumb.
Okay.
So we know how they form, what makes them stable. Let's talk reactions. What do they actually do?
Well, a reactive radical has three basic options we mentioned. Combine with another radical, react with a stable molecule to make a new radical, or just decompose on its own.
Combining sounds obvious, pair up the electrons. But you said that's rare.
It's less common than you might think in typical reaction conditions. Why? Because radicals are usually generated in very low concentrations. They're much more likely to bump into a molecule of solvent or starting material than another short-lived radical.
Okay. But sometimes they do combine, and it's useful.
Definitely. There are some classic named reactions based on this. Take the Pinnacle reaction. You start by adding one electron, maybe from a metal like magnesium or sodium, to a ketone.
Forming that kettle radical anion we talked about?
Exactly. Now, what happens next depends on the solvent. In a prototic solvent, with lots of protons around, it tends to get protonated and reduced further to an alcohol.
Right.
But in an aprotic solvent, no easy proton source, these kettle radical anions find each other and dimerize. They couple up to form a new CC bond. A metal like magnesium often helps here, coordinating two kettles to overcome the negative charge repulsion.
So you can take, like, acetone.
And dimerize it to Pinnacle, which is a 12-Guller2 diol. It's a way to make CC bonds.
And you mentioned a practical use, benzophenone.
Yeah, that's a neat lab trick. If you're distilling THF to get it super dry, you add sodium and benzophenone. If there's no water left, the benzophenone forms its persistent kettle radical anion, which is deep blue or purple.
So the color tells you it's dry.
Exactly. It's a visual indicator. Color disappears if water gets in.
Clever. What about other coupling reactions?
The McMurray reaction is a really powerful one. It also involves coupling ketones or aldehydes, but it uses low-valent titanium. It does a Pinnacle-type coupling first.
To make the diol.
But then the titanium rips the oxygen atoms right off, leaving you with an alkene.
Whoa, CC bond formation.
Yeah. It's fantastic for making sterically hindered alkenes, like tetrasubstituted ones, and it's especially good for intramolecular reactions, closing rings, even medium or large ones that are usually tricky.
Cool. And there was one more coupling. The acyloin.
Right, the acyling reaction. This works on esters. You use sodium metal, and again, you get electron transfer and dimerization. It forms an intermediate alpha diketone, which quickly gets reduced further to an enediolate.
Sounds reactive.
It is. That enediolate can cause side reactions, but there's a brilliant improvement. You add trimethylsilyl chloride, TMSCl, to the reaction.
What does that do?
It acts as a trap. As soon as the enediolate forms, the TMSCl reacts with the oxygens, capping them as stable silly ethers. This prevents side reactions. Then you just hydrolyze the silly ethers at the end to get your product, an alpha-hydroxyketone.
So trapping the intermediate makes it much cleaner.
Much cleaner, much higher yielding. It's a really powerful way to make carbocyclic rings, especially strained ones like four-membered rings, because forming that CC bond is so favorable.
These couplings are neat, but you said the real workhorses are chain reactions.
Absolutely. Radical chain reactions are where radicals really shine in synthesis. They have three key phases.
Initiation, propagation, termination. I remember that.
Exactly. Initiation gets the first radicals going, usually hemolysis via heat or light, maybe using AIBN or a peroxide.
Okay.
Then propagation. This is the cycle. A radical reacts with a starting material molecule to form a product molecule and a new radical. This new radical then reacts, again, keeping the chain going.
So one initiation event can lead to many product molecules.
Thousands, potentially. That's the power of a chain reaction. Finally, termination is when two radicals happen to meet and combine, stopping that particular chain. But if initiation and propagation are efficient, termination is a minor pathway.
Can we walk through an example, like the HBr addition?
Perfect example. Anti-Markovnikov addition of HBr to alkenes. You need a catalytic amount of peroxide initiator, maybe just 1%.
Okay, so the peroxide breaks apart first, or radicals.
Right. That RO then bumps into HBr and abstracts a hydrogen. That's propagation step 1. You get ROH and, crucially, a bromine radical, Br.
Then the Br attacks the alkene.
Yep. It adds to the double bond, and it adds to the less substituted carbon. Why? Because that puts the resulting radical on the more substituted carbon, which is more stable. That's the regioselectivity.
Forming the more stable radical intermediate.
Always follow the stability. So now you have a carbon-centered radical. What does it do?
It needs a hydrogen.
Yeah.
Grabs one from HBr.
Exactly. It abstracts H from another HBr molecule. That forms your final alkyl bromide product, and it regenerates a Br radical.
And that Br goes back and adds to another alkene. The chain continues.
Precisely. It's a beautiful, self-sustaining cycle driven by that initial small spark of radicals.
Selectivity seems key here.
Yeah.
What about halogenating alkenes, like with chlorine?
Yeah, chlorination is interesting. If you react, say, propane with chlorine radicals from Cl2 and light, you get a mixture. About 45% 1-chloropropane, 55% 2-chloropropane.
Why the mix? There are 6 primary hydrogens, but only 2 secondary ones. Shouldn't it be more 1-chloro?
Statistically, yes. But abstracting a secondary hydrogen leads to a more stable secondary radical. That reaction is faster. So it's a competition between statistics, more primary H's, and reactivity. Secondary H is easier to abstract. The reactivity wins out slightly here.
Okay, a balance. What about bromine?
Bromination is much more selective. React isobutane with bron radicals. You get almost exclusively tert-butyl bromide, over 99%.
Whoa. Why is bromine so much pickier than chlorine?
It comes down to the Hammond postulate and reaction energetics. The first step, the hydrogen abstraction by Brna, is actually endothermic. It costs energy.
Unlike with chlorine, which is exothermic.
Right, and the Hammond postulate says that for an endothermic step, the transition state looks a lot like the products of that step. In this case, the product radicals.
So the transition state feels the stability of the radical being formed.
Strongly. Since the transition state resembles the higher energy radicals, the energy difference between forming a primary versus a tertiary radical is really pronounced in the activation energy barrier for bromination.
Making the pathway to the more stable tertiary radical much more favorable.
Massively more favorable, hence the high selectivity.
That selectivity must be useful.
Extremely. Like in allelic bromination, you want to put a bromine next to a double bond on the allelic carbon. That CH bond is weak because the resulting allyl radical is resonance stabilized.
Okay.
The trick is to use N-bromosuccinimide, NBS. What NBS does is maintain a very, very low concentration of actual Br2.
Why is that important?
It prevents competing reactions. If you had lots of Br2, it might just add across the double bond via a radical or even a polar mechanism. Low Br2 concentration favors the radical abstraction of the weak allylic hydrogen by Bra generated from NBS. It's clever control.
Very clever. Okay, switching gears slightly. Functional group changes. What about getting rid of halogens?
Dehalogenation. A classic reagent for this is tributyl tolton hydride, Bu3SNH. It replaces a halogen atom, like Br or I, sometimes Cl, with a hydrogen.
How does it work? Energetically favorable.
Oh, yeah. You're breaking a relatively weak SNH bond and a C-halogen bond, but you're forming a much stronger SN halogen bond and a CH bond. Overall, it's downhill.
And it's a chain reaction, too.
Textbook chain reaction. You need an initiator, often AIBN again, to make a few tributyl tilton radicals, Bu3SN.
Okay, Bu3SN.
That radical abstracts the halogen from your alkyl halide, Rx, giving you our alkyl radical, and Bu3SNX.
And the alkyl radical needs a hydrogen.
And it grabs it from another molecule of Bu3SNH, forming your product RH and regenerating Bu3SNA to carry on the chain.
Nice cycle. Does it work better for some halogens?
Yes. Alkylides and bromides react much faster than chlorides because the Ci and CBr bonds are weaker, easier for the tin radical to break.
And why AIBN is the initiator usually?
Good question. AIBN decomposes to give nitrile stabilized radicals. These are relatively unreactive compared to, say, alkoxy radicals from peroxides.
Why is that good?
Because those AIBN-derived radicals are selective. They will preferentially abstract H only from the weak SNH bond to propagate the chain. A more reactive R radical from a peroxide might start abstracting hydrogens from your substrate or solvent, leading to a mess. Choosing the right initiator matters.
Right, controlling the reaction. Okay, this is all great, but the really transformative stuff came later,
Yep.
right? Using radicals to make carbon bonds.
Absolutely. That really opened up new avenues in synthesis starting around the 1970s. Early attempts, like adding BrCCO3 across an alkene, worked okay, but often had issues. The product radical sometimes just led to polymerization.
Not very controlled.
No. The game changer was using that B3SNH chemistry, but adapting it for CC bond formation.
How does that work?
You start the same way. Generate an alkyl radical RO from an alkyl halide using B3SNH. But before that arcane grab a hydrogen from B3SNH, you want it to add to an alkene, usually an electron-deficient one, to form a new CC bond.
So the radical adds to the alkene first.
Right, forming a new, larger radical. Then that new radical abstracts hydrogen from B3SNH to give the final product and propagate the tin radical chain.
But how do you make sure it adds to the alkene before grabbing the hydrogen? Isn't B3SNH reactive?
That's the crucial challenge. It comes down to concentration effects. You need the radical trap, the alkene, to be present in much higher concentration than the B3SNH, typically at least a 10.1 ratio, often much higher.
So the radical is more likely to find an alkene than a B3SNH molecule.
Exactly. You achieve this practically by adding the B3SNH very slowly, maybe with a syringe pump, to keep its instantaneous concentration low, or by generating it in situ catalytically.
Clever kinetics. Is that the whole story?
Not quite. There's a deeper electronic reason why this works so well, involving frontier orbital effects. It's a really key insight.
Okay. Frontier orbitals. Like HOMO-LOMO.
Kind of like that, but for radicals, the key orbital is the SOMO. Remember the singly occupied molecular orbital?
Right, the one with the unpaired electron.
Okay. We can think of radicals as being either nucleophilic or electrophilic. A typical alkyl radical, ARIA, has a relatively high energy SOMO. It's kind of like a nucleophile. It wouldn't mind donating that electron density.
Okay, alkyl radicals are nucleophilic. What about electrophilic ones?
Those usually have the radical center next to an electron withdrawing group, like a nitrile CNN or an ester, CO2Me. These groups pull electron density away and lower the energy of the SOMO. So these radicals are more like electrophiles. They'd rather accept electron density.
Makes sense. So how does this play into the CC bond formation?
Here's the kicker. That nucleophilic alkyl radical R reacts effectively only with electrophilic alkenes. Alkenes that have electron withdrawing groups like CN or CO2Me attached.
Why only those?
Because of orbital overlap. The high-energy SOMO of the nucleophilic radical interacts very favorably with the low-energy LUMO, lowest unoccupied molecular orbital, of the electrophilic alkene. It's a perfect electronic match, making the addition fast and efficient.
So a nucleophilic radical won't really react with a simple electron-rich alkene.
Not very well, no. The orbital energies don't match up favorably. And conversely, the product radical, which now octene has an electron withdrawing group nearby, is electrophilic. It won't add well to another electrophilic alkene molecule,
But it will react well with
the B3SNH, which is a good nucleophilic hydrogen source. So the electrophilic product radical preferentially abstracts H from B3SNH. This selectivity, driven by frontier orbitals, is what makes the whole process work cleanly.
Wow, that's elegant. It explains the selectivity perfectly.
It really does. It even explains things like alternating copolymerization. If you mix a nucleophilic monomer like vinyl acetate and an electrophilic one like methyl acrylate with a radical initiator.
The nucleophilic radical adds to the electrophilic monomer.
Right. Forming a new electrophilic radical, which then only wants to add to the nucleophilic monomer.
Creating a new nucleophilic radical.
And so on. You get a perfectly alternating chain, ABA, BAB, all because of these frontier orbital preferences.
That's amazing control just from electronics. It really highlights how different radicals are from ions.
Totally different mindset. Radicals rarely add to carbonyls, unlike nucleophiles. They break CH bonds readily, but often ignore polar OH bonds, unlike bases. They abstract halogens, but don't do SN2 substitutions at carbon.
They're soft species, you said. Driven by bond strengths and orbital overlap, not charge.
Exactly. They often ignore the highly polarized parts of molecules that ionic reagents attack, giving chemists a completely different way to manipulate structures.
Now, tin reagents are effective, but they're not exactly environmentally friendly, are they?
No, tin toxicity is a real concern. Thankfully, less toxic alternatives have been developed. One nice one for conjugate addition uses boranes and oxygen.
Boranes. like BH3,
Yeah.
and oxygen from the air.
Yeah, often trialkylbranes like ET3B. Oxygen, which is actually a triplet diradical itself, kicks things off. It reacts with the borane to displace an alkyl radical, an interesting reaction called SH2, substitution homolytic bimolecular, at the boron atom.
Okay, so oxygen starts it, generates R.
That R then adds to your unsaturated ketone or ester, just like in the tin method. The new radical formed then abstracts another alkyl group from another borane molecule to propagate the chain.
And you only need a tiny bit of oxygen.
Catalytic amount is usually enough, often just the oxygen dissolved in the solvent or letting a bit of air in. It's quite efficient and avoids the tin waste.
That's a much greener approach.
Okay.
One last major area, intramolecular radical reactions, closing rings.
Yes, these are often exceptionally efficient, way more so than their intermolecular counterparts.
Why is that? Just because everything's already close?
Pretty much. It's all about proximity. The radical traps say a double bond elsewhere in the molecule is tethered right next to where the radical is forming. Cyclization is often incredibly fast.
Faster than the intermolecular reaction.
Much faster. This means the trap doesn't even need to be that activated. You can cyclize onto simple, unactivated double bonds intermolecularly, which is hard to do intermolecularly.
And does it affect the competition with B3SNH?
Yes. Because cyclization is so fast, the radical is less likely to get intercepted by B3SNH before it closes the ring. This means you can often use higher concentrations of B3SNH if needed, or even use less reactive radical precursors.
Like CCl bonds.
Exactly, or CSVH, C-Cef bonds. Things that would be too slow to react intermolecularly before being quenched by tin hydride can work fine in an intramolecular cyclization because the ring closure is just so quick, it really expands the scope.
What about ring size? Are some favored?
Definitely. 5-membered rings form particularly easily and quickly. 6-membered rings are common too. Smaller rings, like 3 or 4-membered, usually don't form due to ring strain. The transition states are too high in energy. Baldwin's rules for ring closure generally apply here too.
And does the borane-oxygen method work for cyclizations too?
It does, yes. You can use systems like AT3B, O2, and sometimes a different hydrogen donor like hypophosphorus acid, H3PO2, as a non-tin way to achieve these cyclizations. The mechanism is similar. Ag radical initiates, cyclization occurs, and then H3PO2 delivers the hydrogen atom.
Fantastic. So wrapping up this deep dive, radicals are really quite unique beasts.
They really are. Carbon atoms with 7 valence electrons behaving in ways governed by bond strengths, sterics, and these subtle frontier orbital interactions. It lets chemists do things, make connections that are just impossible with standard ionic chemistry.
And they're not just lab curiosities.
Not at all. Think about the environment, biology. Our atmosphere is 20% oxygen, a diradical. They're everywhere, involved in combustion, polymerization, aging, signaling. It's a whole hidden layer of chemistry.
So as we leave the world of radicals, these 7-electron carbons, it makes you wonder, doesn't it? What could be even more reactive, maybe even more elusive?
Indeed. If 7 valence electrons is interesting, what about carbon with only 6?
Setting us up for next time.
Perhaps. Next time we might just dive into the world of carbenes, a completely different kind of reactive intermediate.
Sounds intriguing. Well, thank you for joining us on this deep dive into the fascinating chemistry of radicals.
And thank you for being part of the Last Minute Lecture family.